In this video, we're going to look at another example of work integrals. The question here is to find the work required to pump all the oil out of a cylindrical tank with a height of 2 meters and a radius of 0.5 meters. The oil is pumped out through an outflow pipe 1 meter above the top of the 2-meter tank. Oil has density of 800 kilogram per meter cubed, and gravity is, of course, 9.8 meter per second squared. So we start with y equals 0. This is the bottom of the tank. This is the oil level. Oil at bottom of tank. Y is equal to 2. This is oil at top of tank. Top of tank. Bottom of tank. And the radius of this cylindrical tank is half a meter, 0.5 meters. Gravity is 9.8 meter per second squared. And the density of oil is 800 kilogram per meter cubed. All right, so we start with sketching a diagram and defining some variables. Y equals 0 is, of course, the bottom of the tank. Y is equal to 2 is the top of the tank. These are, in fact, fluid levels of oil. And the radius, R, is equal to 0.5 meters. This is the radius of the cylindrical tank. Density, rho, is 800 kilograms per meter cubed. And G is 9.8. Gravity, meters per second squared. So here we have a diagram. We have the tank at y equals 0. We have y equals 2, the top of the tank. And we have drawn a y equals, this is essentially the level of oil at height y. Now the important thing here is that the distance that every slice has to travel to be pumped out over the top is 3 minus y. Because y equals 3 is this whole distance from here to here. This is y equals 3. And so the distance from here to here is going to be 3 minus y, from the outflow pipe to the level of the oil in the tank. And you can check this. Let's actually check this. We have 3 minus y. So if you plug in y equals 0, the bottom of the tank, we get 3 minus 0. That's 3 meters. That means oil at the bottom of the tank has to travel 3 meters to be pumped out of the outflow pipe. And similarly, y equals 2 at the top of the tank, 3 minus y, we get 3 minus 2 is equal to 1 meter. That means oil at the top of the tank has to travel 1 meter to be pumped out of the outflow pipe. All right. So since the tank is a circular cylinder, this is the tank, it's a circular cylinder, the slices, the horizontal slices, are circular discs of radius 0.5. So these circular cross-sectional slices have a radius of 0.5 meters. So this radius here is 0.5 meters. All right, so the differential volume is equal to pi times radius squared times dy. So pi, that's equal to pi, times 0.5 squared, radius is 0.5, times dy. This is the volume of a thin slice of oil. Now the differential mass, the mass of a thin slice of oil at height y is pi r squared times density times dy. This is equal to pi times 0.5 squared times the density, which is 800, times dy. This is the mass of thin slice of oil, thin circular slice of oil at height y. The differential force, dF, is equal to g times dm. So that's pi times 0.5 squared, pi times radius squared times density, 800, times gravity, 9.8, times dy. This is essentially the force needed to overcome gravity acting on the mass of oil in this thin circular slice. So now let's define dW. dW is equal to 3 minus y, the distance that every slice has to travel to reach the top, times dF. This is equal to pi times radius squared, 0.5 squared, times density of oil, which is 800, times gravity, which is 9.8, times the distance that every slice must travel to reach the top, times 3 minus y, times dy. So this is the work required, dW is the work required to pump out this thin slice of oil out of the outflow pipe 3 minus y meters. From the diagram, we found the work required, dW is the work required to pump out an arbitrary slice at height y, a distance of 3 minus y meters to reach the top, to reach the outflow pipe and be pumped out of the tank. All right, so let's look at step 2. Step 2 is to set up a definite integral and find the work required to pump all the oil out of the tank. So dW, the change in work, is pi times radius squared, 0.5 squared, times density, which is 800, density of oil, times gravity, 9.8 meter per second squared, times the distance that every slice has to travel, 3 minus y, times dy. So work is the integral from y equals 0 to y equals 2 dW. So work is integral from 0 to 2 pi times radius squared, 0.5 squared, times density 800, times gravity 9.8, times 3 minus y, dy. So the work is equal to, now let's pull all the constants out of the integral, and because it's constant, it passes right through the integral, so we get work is pi times 0.5 squared times 800 times 9.8 times the integral from 0 to 2, 3 minus y, dy. All right, so if we simplify this, multiply all these numbers out, we're going to get 1960 times pi, integral from, and let's integrate. What is the antiderivative of 3? That's just going to be 3y, reversing the power rule. What is the antiderivative of y? Add 1 to the exponent, divide by the same number, we get y squared, divide by 2, evaluate it from 0 to 2. So the work is equal to 1960 pi. Put the upper limit in, applying fundamental theorem of calculus, we get 6. Minus 2 squared is 4 over 2, that's 2, minus. Put 0 in, we get 0, minus 0. 6 minus 2 is 4, 4 times 1960, so we get 7, 8, if we simplify, 7840 pi joules. So the work required to empty out all the oil from this tank is 7840 pi joules. If we decimalize this, it's approximately 24,630.09 joules of work that are needed. This is the work required to pump the oil out of the tank. All right, thank you.